In this video, we introduce some useful quantities for studying rectifiable measures called alpha numbers. So given a radon measure mu and a point x in the support of mu and some positive radius r, we let the m-dimensional alpha number of mu inside the ball bxr to equal the infimum over all non-negative numbers c and all affine m-dimensional planes L of r to the minus m minus 1 times the f distance inside the ball between mu and this multiple of m-dimensional Hausdorff measure restricted to L. So recall that a m-dimensional affine plane, so that's just a m-dimensional plane that may or may not pass through the origin. So the alpha numbers quantify how close a measure mu resembles an affine measure in some given ball. So in other words, how close it is to being a multiple of Lebesgue measure along some m-dimensional affine plane. Now, it's not hard to show that there exists an affine measure that achieves the infimum. So when I say affine measure, I mean a multiple of Hausdorff measure restricted to some m-dimensional plane. So in particular, that means that there's some constant c of x at least 0 and some m-dimensional plane Lxr, so that if we define an affine measure curly Lxr to be just this constant c times Hausdorff measure restricted L, then the alpha number of mu inside the ball center x of radius r is exactly equal to the f distance between mu and the measure curly Lxr times this renormalizing constant r to the minus m minus 1. So in short, whenever you see curly Lxr, this denotes the best approximating m-dimensional affine measure to mu inside the ball bxr. Now we go over some basic properties of alpha numbers. So we'll leave the details of these to the reader. So let mu be some radon measure, and let x be a point in its support, and r some positive radius. So first of all, the alpha numbers are always finite. And in fact, the alpha number of mu inside the ball center x of radius r is just at most the measure of this ball divided by r to the m. Now, if we have a ball bys contained in the ball center x of radius r and also centered on the support of y, then the alpha number inside this ball is at most some constant times the alpha number for the larger ball, where the constant is proportional to this power of the ratio of the radii between the two balls. Okay, so the geometric idea is as follows. So let's say this is the ball center x of radius r. Okay, so that means that there is a best approximating affine measure, Lxr. And then if we look at a ball, let's say this is bys. Okay, since mu was approximately Lxr inside this ball, then for balls that aren't too much smaller than this one, the same should hold, okay? But why do estimates get worse as the radius of the smaller ball gets smaller? So let's suppose that the support of our measure, or a measure was, let's say, Hausdorff measure restricted to a very oscillatory graph contained in a small neighborhood of this line. Okay, so the alpha number inside bxr will be small for this measure, and it'll also be small for this slightly smaller ball byx. But notice what happens if we zoom in on a very small ball. Okay, so if we blow this up, okay, now our measure looks like, very nonlinear. Okay, so this is why, even though we may have small alpha number for some ball, as we start zooming in, the plane that was the best approximation for mu inside the large ball is no longer may not any longer be a good approximation of mu inside any smaller ball. And in fact, the alpha numbers can still explode as you zoom in. Finally, the alpha numbers are continuous as a function of x in the support and r bigger than 0. So recall that the alpha number measures the distance between the measure mu and a affine measure inside the ball center at x or radius r. It measures how flat my measure is inside this ball. So, and then recall that, so Lxr was the affine measure of best fit, or the affine measure that best approximates my measure mu inside this ball. Now, if the alpha number is small, that will mean that my measure mu is approximately equal to this affine measure, and that they are close, at least in the sense of the f distance inside this ball. But remember, this is a distance between measures and not between points. So even though the alpha number may be small and the measure mu is very close to this affine measure in the sense of this distance, that doesn't necessarily say that the supports of these two measures are close to each other. So for example, we could have a measure where the alpha number is very small. So that means that the support, or not the support, but the measure, 99% of it, let's say, is concentrated inside a small tubular region of the support of LXR. However, the support of the measure could still be all of Euclidean space. So we could still find points elsewhere in the ball that are nowhere close to the support of the best approximating affine measure. Okay. However, later on, we are going to need to be able to estimate the distance between some points of the support of mu and this plane. So in order to do that, we're going to introduce a lemma that focuses on points in the support of mu where our measure is behaving quite nicely. The points inside the support of our measure that we'll consider are, we'll call them E sub mr. So given a large number m and some radius r, this denotes a set of points x in the support such that for all radii between 0 and r, the mu measure of the ball center x of radius s is at most m times s to the m and is at least s to the m divided by m. So in other words, these are the points where our measure is scaling almost like m-dimensional Lebesgue measure. So the first property that we'll cover says that if x and y are points in EMR, and y is close to x in the sense that it's contained inside the ball center x of radius r over 2, then for any epsilon, there exists a delta so that if the alpha number inside the ball center x of radius r is less than delta, that implies that the distance between y and LXR is less than epsilon r, where recall that LXR is equal to the support of the best approximating affine measure. So in other words, what this says is that if I have a point x, and I look at the ball center x of radius r, and the alpha number is small, then any points inside EMR that are close to x will also lie close to the support of the best approximating affine measure. Okay. Now, for some of the other properties in this lemma that we'll discuss, their proofs will have some elements in common with the proof of this property. So what I'm going to do is actually go through the proof of this property in some detail, and I'll leave the rest of the properties as exercises. Okay, so the first thing that we want to do is define a function f of z. So this will be a one Lipschitz function. I define it to be epsilon times r minus z, the distance between z and y, and then I take the positive part of this function. So I take the maximum of this function with 0. So notice that if the distance between z and y is bigger than epsilon r, then f of z is equal to 0. So this implies that support of f is contained inside the ball center at y of radius epsilon r. Okay, so our goal now is to show that the curly LXR measure of this ball here is positive, since that will then mean that the support of this plane intersects this ball, and hence the distance between y and the support of the plane must be at most the radius of this ball, which is epsilon r. Okay, so let's go through and prove this then. So what I'm going to do is first look at the integral of f d mu. Okay, now really this should be for epsilon small enough. Really for epsilon should be in 0 to 1/2, okay? And the reason why is because I want this ball by epsilon r to be contained inside bxr. Okay, so that means that f is a one Lipschitz function supported in the function bxr. So that means that I can use the triangle inequality with the f metric inside this ball to say that the integral of f d mu is at most the f distance in this ball between mu and curly LXR plus the integral of f against curly LXR. So recall that the supremum of the difference of these two integrals over all one Lipschitz functions f is equal to this f distance. Okay, now notice that if I had a r to the minus m minus 1 times this, this f distance. Let me write that a little bit more clearly. Okay, so if I multiplied r to the minus m minus 1 times this f distance, then this f distance would be exactly equal to the alpha number for the ball bxr. Oops. Okay, now, of course, I don't have an r to the minus m minus 1 here, so that means I have to multiply this by r to the m plus 1, okay? And then furthermore, my standing assumption is that the alpha number is less than delta. So that means that I'm just going to erase this here and replace it with delta. So I have that the integral of f d mu is at most r to the m plus 1 times delta plus this integral here, okay? Now what I'm going to do is bound this from below. So notice that for points inside the ball center at y, radius epsilon over 2, f of z is at least epsilon r over 2 for all z in by epsilon r over 2. Okay, so that means I can bound, so because this integral here, f is supported inside the ball bxr, and in fact, it's supported inside the ball by epsilon r. Okay, so I can use this inequality right here to bound the integral from below. So this is at least the integral over by epsilon r over 2 times epsilon r over 2 d mu. Okay, so this is just equal to epsilon r over 2 times the mu measure of by epsilon r over 2. And now I use the fact that y is a member of the set EMR. Okay, so that means that it satisfies this inequality with with y in place of x here. So that means that this is at least epsilon r over 2 times epsilon r over 2 to the m times m to the minus 1. And this is all at least some constant depending on m times epsilon m plus 1 r to the m plus 1. Okay, so now notice that I have epsilon, some constant times epsilon to the m plus 1 times r to the m plus 1 over here. And on the way other side of the inequality, I have r to the m plus 1 times delta plus the integral of f against this affine measure. So that means that if I pick delta a lot less than epsilon to the m plus 1, that will imply that the integral of f dl xr must be bigger than 0. And then if that happens, that implies that Lxr of the support of f, which is a ball center at y of radius epsilon r, must be bigger than 0. But then that implies that the support of curly Lxr, which is Lxr, intersects this ball. But if it intersects this ball, that means that the distance between y and Lxr must be less than epsilon r, and that proves this property. So the next property says that there exists some delta so that if the alpha number of mu inside this ball is less than delta, so if it's small enough, then the constant cxr, so recall that Lxr is equal to cxr times Hausdorff M measure restricted to Lxr, then this constant cxr is comparable to 1. Okay, so in other words, this constant c is not too close to 0 and it's not too big. The next property says that for points x in EMR and for epsilon less than r over 2, there exists a delta depending on epsilon and m, so that if the alpha number of xr is less than delta, then the mu measure of, for any y in the ball center x of radius r over 2 centered along the line Lxr, the mu measure of the ball center at y of radius epsilon is comparable to epsilon to the m mu bxr. Okay, so maybe let's draw a picture of what this looks like. So here's the ball center x of radius r, and let's say this is the measure LXR, so its support is equal to LXR. So what this is saying is that if we have a ball centered on this line whose radius is epsilon times the radius of the original ball, then the measure of this ball with respect to mu is approximately epsilon to the m times mu of the top ball. So this should make sense. If mu is approximately Hausdorff measure restricted to a plane, then that means that the measure should scale approximately like Hausdorff measure does on a plane. So in particular, Hausdorff measure, if you have a ball of radius r, then a ball of epsilon times the radius contained in it will have Hausdorff measure equal to epsilon to the m times the Hausdorff measure of the original ball. Okay, so in particular, if the alpha number were equal to 0, then we would have equality here because mu would just be Hausdorff measure. But because it's not exactly equal to Hausdorff measure restricted to a plane, this still holds approximately if we have that the alpha number is less than delta. Okay, so this should be seen as a counterpart to property A that we saw earlier. So property A said that for points inside the set EMR, so points inside the set EMR, alpha being small implies that those points are close to the best approximating affine plane. This goes in the other direction. This says that for points y along the best approximating affine plane, their distance is at most epsilon r from the support of mu. And the reason why is because the mu measure of this ball center at y of radius epsilon r is equal to some positive number. So in particular, there must be a point in the support of mu inside this ball, so the distance between that point and y is at most epsilon r. Finally, we have that for points x inside EMR, the alpha number for the ball center x of radius r is at most the conical distance in the unit ball between txr mu and the d cone of m-dimensional flat measures. So this should make sense because the conical distance d1 is measuring how flat the measure txr mu is in the unit ball. But if that measure is approximately flat, that should also say that the measure mu inside the ball center x of radius r is approximately flat. And that's exactly what the alpha number is measuring. So the next lemma that we're going to cover says that we can control the angles between best approximating affine planes for balls that overlap quite a bit if their alpha numbers are small. So first, let's recall what we mean by angles between planes. So if we have two planes, u and v, so m-dimensional planes through the origin, then recall that the angle between these two planes is defined to be equal to the operator norm of the difference between the orthogonal projection onto v minus the orthogonal projection onto u. Okay, so what happens when we have two affine planes? How do we define the angle between those? So the way we do this is we define the angle between u and v to be the angle between the planes u prime and v prime, which are essentially the translates of u and v to planes containing the origin. Okay, so the final lemma that we'll talk about says that if x and y are elements of the set EMR defined earlier, and we suppose that y is contained inside the ball center x of radius r over 2, then the angles between the supports of the best approximating affine measures inside for the ball center x of radius r and the ball center at y of radius r is at most a constant times the sum of the alpha numbers.